Okay, so today we're going to talk about passive seismic approaches for active geophysicists. If you take a look at Wikipedia and look for passive seismic, you will see that passive seismic is a kind of prospection of the subsoil, which relies on multiple measurement points and over periods of and records. I mean, it's supposed to record signal over several hours or several days. And if you take a look at the pictures that they put there, you will see that it's a classic tomographic approach based on, for example, teleseismic events or based on even micro local earthquakes. But today we don't want to talk about this kind of passive seismic. We want to talk about a different kind of passive seismic, which is basically the single station passive seismic. That is what you can do by using a single seismometer, a 3-component seismometer, so a seismometer that records in 2 horizontal axes and 1 vertical axis, okay, and by moving your seismometer around. So we're going to talk about this kind of passive seismic. And this kind of passive seismic relies on the concept of resonance. It's written in the next slide, but okay, I write it also here. So you know that resonance is the behavior that elastic oscillators have when they are excited at a specific frequency. I try to be more precise for those of you who probably forgot this concept. So if you have an elastic object, an elastic oscillator, okay, we typically model these elastic oscillators with 2 simple elements, which is its stiffness, and the stiffness is represented by a spring, and its mass, okay, which is represented by, in this case, this M, this mass. Okay, you know that if you pull these oscillators away from its equilibrium position and you release it, it will start vibrating at a specific frequency that depends only on its stiffness, on its mass, and obviously also on the constraint. Okay, in this case, we use this simple constraint. So the frequency of vibration of this object will be directly dependent on the stiffness, actually on the square root of the stiffness, and inversely proportional to the mass. In other terms, the stiffer the object, the stiffer the oscillator, the stiffer the spring, the larger the resonance frequency of this oscillator. You probably recall from your physics course that this is the graph that tells you what is the resonance of this oscillator. This oscillator will show up a resonance when it's excited at the frequency which coincides with its natural frequency, okay? So we all have experience of resonances, because if you think of many objects, of many common conditions that you see in your daily life, okay, or in the movies, you have certainly seen the glass that is broken by a singer singing, okay, when the singer sings at a frequency which is the same as the resonance frequency of the glass, then the glass can break. You for sure know the Tacoma Bridge case, which was a bridge that collapsed due to a resonance induced by wind. You certainly know the swing, okay? That the principle according to which the swing works is the resonance principle, okay? That the most difficult things for kids is to learn how to push themselves on a swing, okay? And they realize that when they push themselves at the frequency of the swing, then they will start going and going, with larger and larger amplitudes. And you probably know that also what we call the nuclear magnetic resonance in medicine is based on the resonance of the spins of our electrons, atoms, okay? Okay, so let's move to the soils, okay? Also soils under microtremor excitation can be considered as elastic bodies, elastic objects, and we basically model them as spring mass systems, okay? In the case of soil, the stiffness of the spring is linked to the elastic moduli. If I consider the horizontal stiffness, then this will be linked to the rigidity, to the stiffness. If I consider the vertical stiffness, then this will be linked to the Young modulus, okay? And you probably recall that if you're a seismologist, you recall it for sure, that the stiffness is linked to Vs, to the shear wave velocity of seismic waves, and the Young modulus is linked to Vp, to the P wave velocity, okay? So we can say that if we consider the horizontal vibration of this layer, the stiffness will be given in some way by Vs, and the mass will be given by the density of our resonating layer and by the thickness of this resonating layer. Okay, so if we want to interpret the soils in terms of resonances, then we need to use these three things: the shear wave velocity and density and thicknesses. It can be shown, it's quite easy to show that the resonance frequency equation that we gave in this way, okay, the frequency linked to stiffness and inversely proportional to mass, is identical to what is written down here. Okay, we can say that this is the resonance equation for physicists, and this is the resonance equation for geologists or geophysicists. Okay, geophysicists don't think in terms of stiffness, okay, in terms of K, they think in terms of Vs or Vp, okay, depending on the direction of motion. And they don't think in terms of mass, as I said, they think in terms of thicknesses of their layers. But basically, these equations are exactly the same equation. As I said, you can also imagine that your oscillator is put in the vertical axis. Okay, in this case, the stiffness would be controlled by the Young modulus, which is on P wave velocity, and the mass is again dependent on density and thickness. Okay, so I want to show you the first vibration modes of this soil, this this piece of subsoil. Okay, imagine that you have the bedrock here. Okay, here you have the bedrock, and this color object that is moving is your soft soil. This is the shape of the first resonance that so the model shape of the first vibration mode in horizontal direction of your soft soil, which is ruled by this resonance equation. I show you also the vertical, the shape of the vertical, the first vertical mode, which is very easy. Okay, it's just this. And so we basically have that any soil under microtremor vibrates at a frequency which is characteristic, okay, of that soil layer, an horizontal frequency, an horizontal resonance frequency, and a vertical resonance frequency. The horizontal frequency is linked to Vs and to the thickness of the layer. The vertical frequency is linked to Vp and to the thickness of the layer. Okay, they both exist, but as you can imagine, the motion in horizontal direction is much wider than the motion in vertical direction. Okay, so in general, horizontal resonances are much more visible than vertical resonances, just because the stiffness in the horizontal direction is much smaller than in the vertical direction. And not only the amplitude of these two motions is different, but also the frequency, because we all know that VPs are larger than Vs. Okay, they must be larger. They are about 1.7 times larger or 2 times or even more larger. So you normally expect that for a given soil layer, for a given soil layer, the vertical vibration modes of this soil layer will occur at the frequency, which is about twice the horizontal frequency. Okay, so with this concept, we try to see if we can use these equations, these concepts, to do subsoil imaging. Okay, well, if you take a look at this equation, okay, and if you want to do seismic imaging, if you want to explore something about the soil, then you probably agree with me that what we want to find is the thickness of the layer. Okay, I want to go in the field and try to measure the resonances, and I want to try to determine the thickness of the resonating layer starting from the resonances. Or, for example, I can maybe want to assess VP and VS starting from resonances. Okay, it's obvious that if I go in the field and I measure only the frequency, then I have two unknowns, so this system is underdetermined. But if I have a way to constrain one of the other two variables, I can determine the third one. And so this is what we want to do today. We want to try to assess the thickness of our resonating layers from basically the measurement of resonance frequencies. And I'll show you a few ways to do this. So before asking ourselves how to determine the thicknesses of the soils, let's ask ourselves if measuring resonances is easy, okay? Because even if you're not an engineer, maybe you expect that measuring the self-vibrations of buildings must be quite easy because they are fixed only on the ground. and they are free to move on the surface. They are very free because they have the air all around. And that's true. Measuring the resonances of buildings is very easy, okay, compared to measuring the resonances of soils. And normally you see a large number of resonances, like in this case, this is the John Hancock Center in Chicago. But you cannot expect that, imagine that this is the ground level and that you have a number of buildings, okay, of tall and small buildings. Okay, this is the height of your buildings. And if you want to turn this height into frequency, you'll see that tall buildings have low frequencies, intermediate buildings have intermediate frequencies, and short buildings have large frequencies. Okay, so if you measure the frequency, the natural frequency of the building, even if you don't see it, you can say something about its height. Okay, so there's a relation between the frequency and the height of the building, because the height goes with the stiffness of the building itself. So the question is, can we do the same with soils? Because if you think of a soil, think of, for example, a basin, okay, with a stiff bedrock, and then the ground level. If you think of the soil and you think that the bedrock is something very stiff, and which means something that we can consider more or less fixed compared to the soil column over this bedrock, okay? You can maybe see a similarity between buildings and soil, okay? Because here I can imagine that I have something like a short building, a tall building, okay, a very tall building, and so on. So I can work in, I can do this similarity between, let's say, seismic engineering and geophysics. And this is what we're going to do now, okay? So can we exploit subsoil resonances to image the subsoil? Yes, I mean, the answer is yes. I show you here a very nice case, but I want to show you a little more now. The only problem is that if this soil were a building, it would vibrate a lot, okay, and measuring its resonances would be easy. But the soils are here, okay, are not as free as to vibrate as buildings, so their resonances are normally a little bit more hidden, more difficult to detect than buildings' resonances. So in some cases, if you are lucky and you in some geological conditions, okay, it's not a matter of being lucky, but it's a matter of being in specific geological conditions. If you put a seismometer on the ground and you are in some specific geological conditions that we'll see, it's possible that you will see very well the resonances, okay? In this case, we put two seismometers in this basin. You see that it's a basin. And we could see very well the horizontal vibration modes, the resonances in the horizontal directions, which are marked by these peaks in the displacement spectra that we recorded on the ground. And we could also see the vertical motion, the vertical vibration, the vertical resonance, which occurs, as I said, at a frequency which is more or less twice the horizontal frequency. This is linked to the VP-VS ratio. Okay, so if you are lucky, you can see these resonances directly in the spectra, in the displacement spectra that you record on the ground. If you are less lucky, okay, under some other geological conditions, resonances are a little bit less clear, okay, because the exciting function, which is ambient noise microtremor, which has a number of different origins. It originates from sea waves, weather perturbation, volcanoes, okay, peak traffic, and everything like that. So this exciting function is not white. It's stationary, more or less. Okay, so detecting resonances can be sometimes not so straightforward. And so long ago, because it was in the 70s of last century, two Japanese researchers basically observed that if on one side it's true that if you take measurements on a site and you look only at the spectral component, this spectral component of motion change a lot from day to night, from winter to summer, okay, because the environmental noise change a lot. But they realized that if you if you do a very simple operation, which is the horizontal to vertical spectral ratio, okay, you divide the horizontal component by the vertical one or the opposite, okay, the vertical divided by the horizontal, then you get a function which tends to be very stable over time, okay? So this very simple operation of taking ratio is capable to clear the source effect quite efficiently, and it leaves a function which is stable over time at the same site, and which is what we interpret in terms of resonances, okay? Because this function, it has been shown by a number of papers, both phenomenologically and also, I mean, by means of models. This function represents something about the soil, which is basically its eigenfrequencies. Just one note, since we are doing these parallelisms between structures and soils, if you try to use HRV in buildings, this is very wrong, okay? Because if I take a measurement here, for example, in this building, okay, I will have that the horizontal motion is this motion of the structure, okay? And the vertical motion is this motion of the slab. Okay, so if I take these two motions occur at two completely different frequencies, okay? One depends on the elevation of my building, on the height of my building. The other depends on the span of the slab, okay? So these two structural elements are completely independent. And if you take HRV, you basically are mixing up things a lot, okay? You are mixing up a horizontal behavior with a vertical behavior, which doesn't have anything to do with your structural properties. So doing HRV in structures is completely wrong in terms of engineering meaning. But doing HRV on soils is normally accepted for the reason that we have just said, because it's in the same layer, you expect that the vertical resonance occurs at a frequency which is, let's say, twice the horizontal frequency, okay? So they are completely split because the Young modulus and the stiffness modulus are completely different, okay? So it's normally acceptable on soils to take HV ratios to remove the source for this reason, okay? Because if this link between Young modulus and stiffness did not exist, okay? And then maybe doing HRV would not be so acceptable as it's not acceptable in structures. Okay, so we are lucky and we can take HRV, okay? If you are lucky enough, okay, you go in the field, you take a measurement with your seismometer, and you take a look at the spectra, which are down here, and you see these gorgeous resonances in the horizontal components. These two things are the horizontal components of motion, and they show this nice resonance. And if you take a closer look, you will also see that you will spot the vertical frequency, okay, at a value which is twice the horizontal one. And in this case, you also see that we don't have only one resonance frequency, we have two resonance frequencies, okay? And they show up very well, okay? They are beautiful to see in the HRV ratio. Okay, so this stands for soil with different layers, okay? And you have the resonance of one layer and the resonance due to the other layer. There are soils which show more than one resonance. In this case, you have even 4 resonances. Okay, and okay, so historically, these HRV curves have been used in the original sense. Okay, for their meaning of showing resonances. Okay, so they are commonly interpreted as an HV peak is a resonance. Okay, is linked to a resonance. So it's linked to this equation. And the main use of these curves was to produce seismic hazard maps, to produce seismic microzonation maps, maps of resonance frequencies. Okay, this was the original application of the method. I'll show you an example. I took it from the literature. And you see a seismic microzonation map where they basically plotted the frequency, the resonance frequency that they measured at this site. This is a very, very common application. There are also other applications because if you recall always sorry, I take the pen. If you recall this equation, okay, as we said before, if you have a constraint a constraint on one of these two variables, you can determine the other variables, okay? So if you have a constraint, for example, from a drilling or from an MASW, okay, or a dispersion curve that doesn't go much deep, if you have an initial constraint on one of the two variables, you can, for example, determine the VS profile at your site, okay? This was, for example, proposed many years ago. It was 2009 in this, for example, in this paper where VS30 were estimated by using constrained HV measurements. Okay, if you don't have any constraint, you can't do anything. And this was a second application. But beyond the seismic hazard application and these VS30, let's say, applications, people realized that there's much more to do. Basically, they wanted to try to use this technique to image the subsoil. Okay, as I said, there is an inverse proportionality between the frequency and the thickness of the resonating layer. So this means that high frequencies stands for small, short layers, okay, small, short resonating layer, while low frequencies stands for thick resonating layers, okay? So we go from surface to depth, okay? From high frequency to low frequency, we go from surface to depth, as in any geophysical technique. So, and also our HV peaks basically determines the transition, tells us the transition between something soft, a soft layer, and something stiffer, okay? Because the resonance occurs in something soft, which is constrained by something stiffer. So if we rotate counterclockwise this picture, okay, I rotated it so that we have the shallow features on the top and the deep features on the bottom, okay? And imagine that you don't take only one H/V curve, you take several H/V curves, okay? Then if you're lucky, you can map something, okay? By joining the HV peaks, for example, you can start seeing a kind of seismic reflector. First, in terms of frequency, because the direct information that you get is in terms of frequency. But as I said, if you have some kind of information about a possible VS pattern, a VS geometry, okay, at your site, you can move from the frequency domain to the depth domain, okay? So you can move your HV curves basically from the frequency domain to the depth domain. This is what is shown here. This application is not, I mean, this example is not the first one. Of course, this method was proposed 25 years ago by these two German authors in the Rhine Basin in Germany. And this was the first attempt to link the resonance frequency to the depth of the sediment to bedrock contrast at the Rhine River basin. Things evolved, okay, from that time, the way to plot the data, the way to emphasize the reflectors and so on, so you can get such wonderful pictures, okay? This is an imaging of the Mugello Basin, which is in northern Italy, actually, it's in Tuscany. And you see that we explored 5 kilometers, and a section of 5 kilometers, just by taking of HRV recordings at these sites, okay? And we had the VS model because we measured VS with dispersion curves at some parts in the basin. And so we managed to get this wonderful imaging of the Mugello Basin at this cross-section. This is another example, it's even more interesting, okay, of another reflector mapped by using HRV. This is another case of a very deep reflector, because in this case we are speaking of 600 meters, okay? So it's quite a big basin, again, in northern Italy, over a size of 2 kilometers. And this is another example, this is the example that I showed you before, of another reflectors mapped in this site, which is in UK. I found on the web other examples of reflectors mapping in in mine and ore exploration. This is a very old example that we did many years ago, for a tectonic study. We were interested in mapping the bedrock depth in this part of Italy. And this method is also used to map landslides, okay? If you have, this is a landslide that we have in central Italy, quite a big landslides, and they applied several techniques. One of these was HRV to map the transition between the slide and the stiff bedrock. Okay, so far so good. Okay, we have discussed the nice applications of HRV, but I want to point your attention on a further topic, I mean another element which can help you understanding HV curves in other geological conditions. So let's take a look at these two HV curves. Okay. I mean, if you take a look only at the HV curve, okay, they show a peak, one at 0.6 hertz, one at 0.3 hertz, okay. This peak seems to be a little bit larger than the other one, but I mean, they are normal HRVs, okay. But if you take a look at their spectra, at the spectra from which they derive, then you'll see that these spectra are completely different, and completely different is their meaning, in the sense that this HRV peak here, sorry, is linked to a minimum in the vertical spectral component. Okay, so I have an HV curve where the HV peak is linked to a minimum in the vertical component. On the other side, I have an HV peak, which is on the opposite linked to a maximum in the horizontal components. Okay, so here I have a minimum in the vertical component. Here I have a maximum in the horizontal components. Okay. These two things are completely different in terms of interpretation and in terms of geophysical meaning, okay? In the sense that if I ask you, which one you expect to be a resonance, I'm sure that you would say this is a resonance, because a resonance is an amplification of motion at a specific frequency, okay? So here, I clearly see the amplification of the horizontal component at 0.3, 0.4 hertz. Okay, so this is the resonance. The other one is not a real resonance. Okay, the other one is linked to a minimum in the vertical component. And a minimum, I mean, a lack of wave is not a resonance. Okay, can't be a resonance. A lack of wave is, I mean, this feature, which is actually more common, because if you take a look at your HRV, if you have some, you'll see that the wide majority of HRV is linked to minima in the vertical component, not to maxima in the horizontal component. This feature is linked to surface waves, okay, and specifically to the Rayleigh wave and its the amplification at the frequency that coincides with the SH resonance frequency at, with the SH resonance frequency. Okay, so on one side we have an HRV which is linked to basically Rayleigh wave, and on the other side, we have an HV feature which is linked to a real resonance, that is to SH waves, okay? So if you have a database of HV curve and you have never taken a look at their spectra, I invite you to take a look at the spectra, and you'll see that in the most part, in the majority of cases, you'll have things like this, okay? Your HV curves will be linked to surface wave phenomena. And this is good because as long as HRV are linked to surface wave phenomena, then the capability of HRV to map your seismic reflector is warranted, okay? Because now we don't have time to enter in the details of theory, but as long as what you see is a phenomenon linked to surface wave trapping in layered media, then you can be sure that you'll be able to image the subsoil like this and to get these wonderful pictures of your subsoil. On the other side, when you start seeing, sorry, I go here. When you start seeing real resonances, so peaks in the horizontal components, then you might be a little bit disappointed, because if you take several measurements, for example, like here across a basin, you will see that your HRV will no more be able to map your reflector, okay? It will start showing a fixed resonance, okay, a fixed value at all your sites. And it won't be able to image your subsoil anymore. Why? Well, the explanation is quite easy, because if you think of a resonance, okay, if I take this basin, okay, and I take this section, this slice, okay, in my basin, and I imagine that I take a number of measurements across this basin, okay? What is the shape of the what's the shape of the resonances that I expect? This would be, oh God, I want to, okay. This would be what we call the longitudinal vibration mode, okay? This is you see the vibration mode along the longitudinal axis, this one. And this would be the God, there's no way to, sorry. I try with the no. Well, I cannot, 1 second. I try again, okay. No, there's no way. Okay, anyway, this would be, so maybe I have to change the pointer, but I don't know how to do. Okay, you have to imagine them, sorry. This would be the longitudinal mode of vibration, and this would be the transversal mode of vibration. Okay, so you have one longitudinal motion like this. Let me clean. Okay, one longitudinal motion like this, and one transversal motion like this. Okay, and if you take a look at this picture, you will see, or if you recall how it was moving. Now I can't make it move. Oh, okay, it's moving again. Good. If you take a look at this movie, you will see that if you change point, okay, acquisition point along your cross section, the frequency of motion doesn't change. Okay, the amplitude of motion change, because the amplitude of motion is small, close to the boundaries, and it's large in the center of your basin. And the same applies to, let me see if I can make this move. No, okay. And the same would apply here, okay? You would have some points that move a lot and some points that are more or less fixed. But what changes is the amplitude of motion, okay? It's not the frequency. So when you are seeing real resonances, you don't expect to see variations in frequency, because if this is an elastic body, okay, if this is an elastic body, it moves as an elastic body, it moves at all sides with the same frequency, and only the amplitude change. Okay, so this is the characteristic. If you think of a swing, the swing doesn't change frequency along the rope. Okay, the frequency is always the same. It's the amplitude that change. Okay, so it's absolutely normal for a real resonance that a real resonance cannot track your subsoil reflectors, because they are unique value that represents the geometrical distribution and the mass distribution of your cross section. Okay, so if we go back to these two cases, okay, as long as you are using or you are seeing HV curves based on surface waves, that is HV curves where the HV peak is linked to a minimum in the vertical component, then in imaging sense, you're lucky, because it means that you'll be able to track your geometries. On the other side, if you start seeing real resonances, that is resonances linked to SH waves or to P waves, okay, then in this case, you won't see the HV peak moving anymore, because it's not, I mean, a resonance doesn't change in the different part of your body, okay? It's a unique value for your entire body. So what makes these things visible, or these things, I mean, what is the difference? When do I expect to see Rayleigh waves dominating compared to body waves dominating? Well, the answer is quite easy, in the sense that the smaller the aspect ratio of your basin, so of your layers, okay, the more your layers are horizontal or your basins are large and shallow, the easier it would be for you to see HV curves based on surface wave, with surface waves dominating. On the other side, the more your geological structures are narrow and deep, then the more you will be seeing real resonances. Okay, so you can already expect, depending on, now I give you a plot so that you can better discriminate the two cases. Okay, so this case is good. Okay, we can do everything. What can we do in this case? Is there anything that we can do in this case to understand something about the subsoil? Well, I want to show you, sorry. I want to borrow a couple of elements again from engineering structures to show you that also in this case, you can say something about your geometries, okay? Even if you can't map them with these wonderful pictures as in the previous case. So can we still use the model frequencies to assess something about our geological structures, also when we are seeing real resonances? The answer is yes. Just give me 5 minutes and I show you how. Okay, so as I said, I want to borrow a couple of elements from engineering. So think of a building. Okay, this is a building. And these are the vibration modes of the building. Okay, this is of a shelf. This is the first mode, the second mode, the third mode. It can be shown that the slenderer your building, okay, the larger will be the distance between the higher modes. The thicker your building, the shorter will be the distance between your higher modes. I show you an example here. Consider this slender structure, which is a pillar of a bridge. These are the modes, okay, the frequency of the higher modes. And you see that if I take the ratio between the frequencies of each mode and the frequency of the fundamental mode, this distance is large, okay? If I move to a thick structures and I do the same, you will see that the distance between the modes is shorter, okay? So the first element that we can use when we see real resonances to assess something about the slenderness, which is about the aspect ratio of our basin, is to compare the higher modes frequencies with the fundamental mode frequencies. This is a good indicator of slenderness or thickness of our geological structures. There's something more that we can do. Since I'm in Venice now, I took a picture of Venice. In Venice, for example, this is San Marco Square. You have probably been here. If you consider the San Marco bell tower, okay, you see that it has a square cross-section. If you take this, which is called Procuratia, it's a big building, okay, you see that its section is completely different. This is a very elongated structure, okay? So you expect that if you take a measurement on a square structure, you will see the same frequencies in the two directions, in the transversal and in the longitudinal direction. If on the other side, you take a measurement on a long, elongated structure with very different stiffnesses in the two axes, then the transversal and longitudinal motion will differ a lot, okay? And this is exactly what you see, because if you take measurements on the San Marco bell tower, you see that the resonances in the two main axes are identical. They are both at 0.7 Hertz. If you take a measurement here, you'll see that the behavior in the two orthogonal direction is different, okay? And you have a soft, let's say, a stiff axis and a less stiff axis, okay? So in this case, the comparison between the transversal motion and the longitudinal motion, again, tells you something about the stiffness distribution and the geometrical distribution of your masses, okay, and stiffness of your objects, okay? So can we apply this to concept? Can I use the transversal to longitudinal ratio or the higher modes frequencies versus fundamental mode frequency to understand something about the subsoil, even when the subsoil is, the HRV is showing real resonances, okay? And I cannot image my reflectors anymore? The answer is yes. Okay, a few years ago, we did a quite extensive numerical study. We made models of many kind of basins. Okay, if you are interested, I mean, the link is this is the paper, or I can send it to you. Okay, so we made a numerical model, a big set of numerical models. And we basically studied the sequence of higher modes. In this case, the longitudinal mode. So you see the longitudinal mode of a typical basin, and you see the typical modes of a transversal, the typical shapes of transversal modes. And we provided a number of relations that link your, for example, transversal to longitudinal modal frequencies with the aspect ratio of your basin, where the aspect ratio is the ratio between the thickness, the maximum thickness, and the half width of your basin, okay? So you see that when you are in conditions where, when you are in low aspect ratio basin, these transversal to longitudinal frequencies are very similar. As long as you move away from, low aspect ratio, as long as you move to large aspect ratio basins, or not only basins, okay, it applies also to other structures, then you'll see that the transversal to longitudinal motion becomes larger, okay? And since measuring, I'll show you in a while, measuring transversal and longitudinal frequencies is quite easy, assessing transversal and longitudinal frequencies is quite easy, you have an immediate indicator of the aspect ratio of your basin, just comparing the transversal and longitudinal modal frequencies. We provided a number of other plots. Now I don't want to go in detail with this. We've also provided a number of plots that lets you assess the equivalent velocity of your basin. Okay, again, by using this modal frequency ratio, you can have an estimate of the equivalent VS over VP of your basin. And I show you a couple of examples, so maybe it's easier for you to understand. I take some examples from the Italian Alps. Okay, so we are here in the Alps. In the Alps, we have a number of big rivers, and I show you some examples from this river, which is called the Adige River, the Adda River, and the Piave River. So let's start from the Adda River. You see that this is the basin of the Adda River. We studied a number of cross-section, okay, by taking the measurements along the cross-section. And this example comes from there. And in this case, we were in an absolutely dominating body wave condition because we could measure the transversal and longitudinal modal frequencies very well. Okay, they were absolutely well determined. And okay, we spotted even higher modes, but I'm not going to talk about them. Also by taking even not synchronous measurement, okay, they can also be non-synchronous measurement. You can even reconstruct the mode shapes. This is the mode shape of the first mode, the modal shape of the second mode, and reconstructing the modal shape is also important if you want to assess asymmetries in your basin. Anyway, so by simply looking at this transversal to longitudinal ratio, and also possibly to other ratios, by using this chart, okay, we managed to assess that we had the ratio between the transversal motion and the longitudinal motion, which was of 1.22, which stands for an aspect ratio of our basin of 0.5. Okay, so we basically assessed that our basin was about 500 meters thick, and the equivalent VS was 640 in this meter per second. In this basin, we also had information from seismic reflection, so we could compare our results. You find these examples in that paper. I move quick to another case, again in the Alps. This is the wonderful Bolzano Basin, the Adige River Basin, which is the second longest river in Italy. And also in this case, we managed to see in the spectra, in the individual spectra, gorgeous resonances. Okay, these are absolutely wonderful. They are absolutely stable, and wherever you measure them, they are wonderful to see. And again, if you work in terms of transversal to longitudinal or higher modes versus fundamental mode frequency, I go back here, you can assess, okay, in this case, we also rebuild the modal shapes. In this case, we assessed that the aspect ratio of our basin was a little bit lower than the case before. In this case, it was 0.4, and we managed to assess the maximum thickness and the equivalent VS. Just for you to know, in this basin, we also installed a permanent station, and so we managed to study 5 years of data, and we could see how these resonances change. They have a periodicity and a yearly periodicity, and even a daily periodicity, okay? You probably know that people are studying the relation between water content and these things. Honestly, I don't think that a daily periodicity is linked to water content, okay? It's probably linked to astronomical factors, to the moon load and these things. But anyway, you can clearly observe periodic oscillations, very small, okay, of the resonance frequencies in these basins. In any case, the resonances are absolutely clear and stable. And show you a last example. Okay, this is a smaller river in Italy, the Piave River, and it's a wonderful place. Also, in this case, we managed to assess the transversal and longitudinal motion by simply taking a measurement at a few points across our basin, and we managed to use our plots again to assess this. This is a smaller aspect ratio basin. In this case, it's 0.3, the aspect ratio, and the thickness of the basin is much smaller, and also the equivalent VS. So I go back, sorry, I wanted to go back 1 second here. sorry. So when no, sorry, I wanted to find the picture, but I think it's in the end. Okay. So what we did in this case, okay, in the case when we see real resonances, is something similar to what this mathematician asked himself in 1966. He published in the American Monthly a paper asking himself if it was possible to hear the shape of a drum, meaning that can I assess the shape of a drum by the noise it makes, which means by the resonances it produces, okay? Because I mean, if you play music, you know that music is based on resonances, okay? So can I assess the shape of my drum from the resonances that I produce? And we basically did the same thing. Can we hear the shape of our basins when our basins show only two-dimensional resonances and HRV cannot work anymore? Okay. So the answer we gave is, yeah, I mean, yes, you cannot do as beautiful imaging as with HRV when they are dominated by surface wave, but you can still do something. And specifically, you can still assess the aspect ratio of your basin, and which means the maximum depth. You can also have a good estimate of the equivalent VS, which is maybe good for your seismic hazard studies. Clearly with uncertainties linked to the wavelength that you use, but this is physics. I mean, this is not HRV. This applies to any technique in physics. Okay, so going back to the conclusions, okay. Next time, if you are not used to do that, when you take your HRV, microtremor recordings, don't forget to take a look at the spectra, at the individual spectra, because, because if your individual spectra are dominated by a minimum in the vertical component, okay, then you are probably in a surface wave dominated case. And in this case, you can be sure that you get wonderful images of your subsoil. If on the other side, you start seeing big resonances, okay, no minimum in the vertical component and nice peaks in the horizontal one, and this in the horizontal components, and these horizontal components are also different in the transversal and longitudinal direction, then you are in a, let's say, body wave dominated case, okay? Then you are seeing the real resonances of your geological object, and these resonances are not expected to change with the position of measurement, okay? Because they are real resonances. Anyway, if you still want to use these things to do some kind of imaging, then try to think in terms of transversal to longitudinal ratios or higher modes versus fundamental mode frequencies, exactly as people do in structural engineering, for example. Okay, so this was a kind of summary. I don't know if someone is going to give you the slides. I put these things in case someone is going to give you the slides. And I stop here. Thank you very much for your attention. And